We are almost nearing towards the end of this course, which means we are going to kind of do the same thing that we did for the BJTs, but just finish it up for the MOSFETs. So we're going to make an equivalent circuit model. Now for the BJTs, we know that the equivalent circuit helped us do some small signal analysis. Now we can do a similar thing for the MOSFET, and the equivalent circuit model that we get is given here on the right. So notice here with the lowercase letters, that's going to signify the small signal as opposed to capital letters that will signify the large signal or DC signal. So we see here we have the gate and the source on the left here, and we're going to have a dependent current source that's going to be equal to the transconductance times that small signal voltage from the gate to the source. Now we're also going to have some resistance or some drain resistance. Notice that this is not RDS on. And then some total drain current, and then we look at the drain to source voltage, which is going to be VDS. Now recall what our equation was for the transconductance. In the last video, we defined that Q point, fairly similar to our BJTs and even our diodes. So what we're going to do is consider just a generalized FET circuit, and we can say that the drain current is equal to some DC or Q point drain current, and then we have this AC component, or this small signal component. Now that drain current is going to be due to the gate to source voltage, and with that voltage we're going to have some DC or large signal part and then some small signal part right here. Now for saturated, we know that we can represent the drain current like this, or again recall what K is from the previous videos, and we have our threshold voltage, which would be defined by the datasheet. Now if we express this drain current in terms of this current up here, we get this term here on the left, and then on the right hand side we simply replace VGS with the time dependent version, and that gets us this. Now we can expand this whole term out to arrive at this term, and notice here in this first term that that's actually going to be equal to the Q point drain current. Now because we have that on the left hand side and on the right hand side now, we can just subtract these, and what we're really left with is the small signal component. So we have lowercase id as a function of time. We get that middle term up above, and then we get that last term. Now if we have some small signal as we're assuming, we're going to make kind of another bold approximation where we say that this VGS squared term is much smaller than this term, such that we can kind of ignore this and we're just left with this bottom term. Now if we recall what our value for that transconductance is, well, we know that's also equal to 2 times the square root of K times the square root of the Q point drain current, and we know what that drain current is at the Q point, so we can again make some substitutions, and what we arrive at is that the drain current for that small signal is approximately equal to the transconductance times the small signal gate to source voltage. We can also be a little bit more precise, and we can set up a different model. If we set up a model like this, where we are going to set a KCL node right here, we can say that the current going in, I sub D, that's going to be equal to the current going out. So we have the transconductance times the small signal gate to source voltage, that's this current right here, plus this current, which is going to be VDS divided by lowercase rd. Now from this equation, if we set VDS equal to 0, we can simply say that the transconductance is equal to ID divided by VGS. Now recall that all of the variables in the lowercase are centered about some Q point. So if we say that the lowercase VDS is equal to 0, it's really saying that for the whole system, we are at the Q point of VDS. Now since we know that the gate to source voltage will change a little bit and it will change the drain current just slightly, well, we can say that the transconductance is actually approximately equal to that small change in the drain current divided by that small change in the gate to source voltage, and this is all going to be at the Q point for VDS. Now if we come back to this equation and we set VGS equal to 0, or at some Q point, well, we can set up this relation where we have 1 over RD is approximately equal to the differential in the drain current, and then that's divided by the differential in the drain to source voltage, at VGS being equal to the Q point or VGSQ. So if we scroll down to the characteristic plot, what does this actually look like? Well, let's say that we have some Q point right here, and that's going to be at VGS is equal to 3.5 volts. And let's say from being able to find IDSQ, we're able to find VDSQ. So we know our Q point for VDS. And we know as VGS changes in the small signal, that the drain current is also going to change. So let's say we have some range here. So if we know how much VGS is changing, we should be able to calculate how much ID is changing, and then we can just divide those to get the transconductance. Now, to find this resistance, we're going to set VGS equal to that Q point. So again, let's say that Q point is at VGS equals 3.5 volts. Now what we can say is in the saturation region, we can really pick any point. Ideally, this would be a flat line, but we might see this linear ramping to some shallow nature. So we know what our range for ID is, and we can actually modulate our drain to source voltage, and then we can divide those two to get the inverse of this resistance. Now let's say VGSQ is equal to 2.5 volts, and we were looking at how ID changes if we change VDS. So let's say we have a flat line here. So we don't really say that ID is changing at all. So we would say that 1 over RD is approximately equal to 0 over VDS. And if we actually flip this, we would find that RD tends towards infinity. Now if we scroll back up here, if this RD tends towards infinity, it kind of acts like an open circuit and it can be ignored. So now we can simplify this model if we have the ideal settings. But nevertheless, that's how we define these parameters. In the next video, we'll look at an amplifier circuit, and that should answer any questions that this video may have left. Thank you for watching. If you learned anything, found anything useful, please like, comment, subscribe, share. It helps me crawl out of the YouTube algorithm. Thank you for watching, and we'll see you in the next video.